Welcome to the Speaker Odyssey 2020. This is the tutorial session on text-to-speech synthesis. I'm Wang from National Institute of Informatics, Japan. I'm going to lead you through this tutorial on text-to-speech synthesis. First, a brief self-introduction. I'm a postdoc at Informatics lab. I got my PhD 2 years ago from a SIB lab. During my PhD, I was working on text-to-speech synthesis. Since the postdoc, I have been working on speech and also music audio generation. Meanwhile, I also get involved in the ASV Spoof 2019 and the Voice Privacy Challenge this year. For this tutorial, I'd like to first apologize about the abstract. I think in the abstract I mentioned I will explain the recent neural network-based acoustic models, waveform generators, the classic hidden-Markov-model-based approaches, and also words conversion. But this abstract seems to be too ambitious. I think I can't cover all the topics in 1 hour tutorial. So in this tutorial, I will focus on the recent neural network-based acoustic models, including the Tacotron and its variants. For other topics, such as the waveform generators and HMM, I have to leave them out from this tutorial. But if you are interested, you can find useful notes and the reference papers in this slide. For this tutorial, I'm going to focus on the recent approaches like the Tacotron and the related sequence-to-sequence TDS models. I'm going to talk about how they work and what are the differences. So this tutorial is based on my own reading list. I summarized what I have learned and what I have implemented with my colleagues. So the content might not be comprehensive. However, I will try my best to include more contents. I will summarize them in the notes in each slide. And also I provide an appendix and reading list with what I have read in the past. So I hope you can enjoy this tutorial, and of course your feedback is welcome. So for this tutorial, I'd like to first give a brief introduction about the current situation or the state of art of the TTS research. After that, I will give an overview of the TTS, briefly introducing the classical methods and why we are here today. After that, I will spend most of the time of this tutorial on the sequence-to-sequence TTS, the state-of-art TTS nowadays. I will explain different types of sequence-to-sequence TTS, those based on soft attention, hard attention, and hybrid approaches. And finally, I will make a summary and draw a conclusion. Let's begin with introduction. TTS is a technology that converts the input text into the output waveform. One famous example of a TTS application is a speaker used by Professor Stephen Hawking. Nowadays, we have more types of applications based on the TTS. One example is the intelligent robot. We also have the digital assistant, our cell phones and computers. Research on TTS has a really long history. If we read the books and reference papers on TTS, we can find so many different types of TTS methods, format synthesis, unit selection, and WaveNet. The reason why researchers are still working on TTS is that researchers want to make the synthesized speech as natural as possible, as natural as human speech. For some types of applications, we also want the synthesized speech sounds like us. So towards this goal, research has put so many efforts into the TTS research. However, it was not until the recent years that researchers found really good models to achieve this goal. Here, I'd like to use the ASV Spoof data to show the rapid progress of TTS. First, it's a picture of the ASV Spoof 2015, the I-vector space where we show different types of TTS system and their distance from the natural speech or genuine speech. So you can see there are many systems here. Most of them are based on HMM or GMM-based words conversion. For this HMM-based TTS is really far away from the natural speech. It's only the unit selection that is close to the natural speech. So, how about ASV Spoof 2019 after 4 years of research? Here's the result based on X vector. Compared with the picture in 2015, we can see there are so many systems that are really close to the natural speech. Not only the unit selection, I'd like to give the example here. The first example is the HMDN system, as you can see from the screen, which is still far away from the natural speech. The unit selection is still close to natural speech. Meanwhile, we can see other types of TTS methods, including the sequence-to-sequence TTS and the WaveNet. So they are really close to natural speech. Of course, this figure based on acoustic features, either the X vector or the I vectors. But the question is, how do the synthesized speech sounds really like in human perception? To show that, to answer that question, I'd like to use the results from our recent study where we conducted human evaluation on the ASV Spoof 2019 data. Here, we ask human evaluators to evaluate how the synthesized speech sounds like the target speakers, and how the synthesized speech, what is the quality of synthesized speech compared with the natural speech. So we show the results in terms of it by using the DET curves. As you can see from the left-hand side, we can see the HMDN is really far away from the natural speech in terms of the speaker similarity. So the score distribution is far away from the natural target speech. Unit selection is closer, but still not close enough. It's only the sequence-to-sequence system, as you can see from this picture, and it's really close to the target speaker natural speech. So in this case, the ER is close to 50%. So which means this system can really sound synthesized speech sounds like the target speakers, and human beings cannot tell them from each other. It's a similar trend if we look at the results in terms of speech quality. DN and the unit selection are not good enough. It's only a sequence-to-sequence model that is really close to the natural speech. So from these results, we can have a general idea on how the recent models based on the sequence model improve the quality and the speaker similarity. And even the human beings cannot tell them from the natural speech. Okay, after introducing the results, I'd like to play some samples from the ASV Spoof 19 database. And I think you can have a general perception on how the latest model sounds like compared with natural speech.
We did not compete with any other local farmer. We did not compete with any other local farmer. We did not compete with any other local farmer. We did not compete with any other local farmer.
A friendship that will endure. A friendship that will endure. Friendship that will endure. A friendship that will endure.
So these are the samples from two speakers. I think you may agree that the unit selection sounds like the natural speech in terms of the speaker identity, but you can sometimes perceive the jump when we concatenate the different units together. The DMM sounds smooth, but it sounds like artificial speech. It's the sequence-to-sequence model that sounds really like the target speakers. If you are interested, you can find more samples on our website or download the ASV Spoof 19 database to have a judge. After listening to the TTS samples from ASV Spoof 2019, I'm going to talk about more details on the TTS, what kind of problems we may face when we build a TTS system, what kind of solutions we can use, and how we come up with the idea of the sequence-to-sequence TTS models. So what are the problems we may face when we build a TTS system? To give you an example, here is one sentence from the guidelines for topic labeling, Mariana made marmalade. The first thing we need to notice when we convert the text into the waveform is that the text is basically discrete, it comes from a finite set of symbols, while the waveform is continuous in time domain and also in the value domain. So because of the basic difference between the text and the speech, the first thing we notice is the ambiguity in pronunciation. For example, the A-made sequence, the Mariana or made, they are pronounced in different ways. The second thing is about alignment. For example, we may say made, we may say made. We may short or increase the duration of the sound when we pronounce it. So this kind of alignment we need to learn from the data, which is not easy. Another issue is to recover information which is not encoded in the text. For example, the speaker identity and the porosity. These are really difficult issues when we build the TDS systems. Here is one example of using classic TDS to convert the text into the output waveform. So the first step of the system is to clean the input text, to do some kind of text normalization, to remove all kinds of strange symbols from input text. So after that, the system converts the text into the phoneme or phone strings. So the phone or phonemes are symbols that tell the computer how to read the word. Of course, this is not enough. We may need to add additional prosodic tags to each word or some part of the word. For example, we may emphasize the Mariana instead of the maid. So giving the linguistic information about how to read the text, the system will convert them into the acoustic units or acoustic features. Finally, the system will use a waveform generator to convert the acoustic information into the output waveform. In literature, we normally refers to the first steps of the TDS system as the front end and the rest as the back end. In this tutorial, I cannot cover the topics on the front end, and the readers can find the 2 textbooks on front end. For this tutorial, we focus on the backend issue, especially on how we learn the alignment between the text and waveform in the backend models. The first example I'd like to explain is the unit selection based backend. So as the name suggests, this method is quite simple, straightforward. For each input unit, we just directly select one speech segment from large database. After that, we just directly concatenate the speech units into the output waveform. So there is no explicit modeling of the alignment between the speech and the waveform because this alignment has been preserved in the speech unit. So we don't really care about the alignment in this kind of method. However, the story becomes different when we use the HM-based backend to synthesize speech. So unlike the unit selection, which directly generates waveform, for HTS, HM-based approach, we don't directly predict the waveform. Instead, we first predict the sequence of acoustic features from the input text. So these acoustic feature vectors, each vector might corresponding to, say, 25 milliseconds of the waveform. And we can use a vocoder to reconstruct the waveform from the acoustic feature vectors. So in each acoustic feature vector, it might contain the, for example, the capstone coefficients, the F0, and other kind of acoustic features specific to the speech vocoders. But this is a general idea. In HTS, we don't directly predict waveform. Instead, we need to first predict the acoustic feature vectors from the input text. The question is, how can we do that? Remember that the input information has been extracted from the text, including the phoneme identity and other prosodic tags. So in HTS, we normally encode or convert the linguistic features into a vector for each input unit. So in each vector, it may contain information like the phoneme identity, whether the current syllable is stressed or not. So we assign this kind of vector for each unit. The question, of course, is how can we convert the sequence of input linguistic vectors into the output acoustic feature vectors? So remember, the number of vectors we have is equal to the number of units in the text. And this number is much shorter than the number of acoustic feature vectors we need to predict. So this is an alignment issue. This is how the HTS system handles this issue. Since this system is based on HMM, so the first thing we need to do is to convert the linguistic vectors into the HM state. So this is done by simply searching through the decision trees. After that, we can get the HM state for this specific vector. After we searching and finding all the HM state for each linguistic vectors, the next thing is to predict the duration for each HM state. For example, when we repeat the first HM state 2 times, the second one 3 times. Given this duration information, we can create a HM sequence like this. So remember that the sequence of this HM state will be equal to the number of vectors we need to predict in the output. Thus, the regression task becomes much easier because we can use many types of algorithm to generate vectors from each HM state. Specifically, HTS system use the so-called maximum likelihood parameter generation algorithm to produce the acoustic feature vectors from the HM states. But this is how the HTS system produces the output from the input linguistic feature vectors. To briefly summarize the HTS system, we can use this picture. So we generate linguistic features from the input text. We do the searching in the decision trees. After that, we predict the duration for each HM state. So this is where the alignment is produced to generate output acoustic features. After that, everything is straightforward. Just convert each vectors into the output vectors and do the waveform generation using the vocoder. From HTS to DN is straightforward. We just need to replace the HM state with the neural networks, feedforward one or recurrent one. However, for this kind of framework, we still need the duration model. We need to predict the alignment from the linguistic feature vectors. Without that, we cannot prepare the input to the neural networks. Indeed, as the paper by Alex Graves says, RNNs are usually restricted to the problems where the input and output sequences are well aligned. As long as we are using the common feed-forward or recurrent neural networks, we still need additional tools, including the HMM, to learn and generate alignment for the TTS task. We may wonder whether we can use a single model to jointly learn the alignment and do the regression. And this is where the sequence-to-sequence model comes to the stage. In fact, they are more ambitious. They wanted to use a single neural network to jointly learn the alignment, do the regression, and even conducting the linguistic analysis on the input test. And there are lots of recent work showing that this approach is reasonable, and it releases the power of neural networks so that we can achieve a better quality for TTS. Okay, let's look at the sequence-to-sequence TTS models. Remember that the task of sequence-to-sequence model is to convert the text into the acoustic feature sequences. And we need to solve 3 specific tasks: how to derive linguistic features, how to learn and generate alignment, and then how to generate output sequences. Again, we cannot use the common neural networks such as the feed-forward or recurrent one. For this kind of sequence-to-sequence model, we normally use attention mechanism. For explanation, I will use X as input while Y being the output. Notice that the input has m time steps while the output has n time steps, so they have different time lengths. The first framework we can use is the so-called encoding and decoding framework. Here we use an RNN layer as the encoder. We process the input and extract the C vector from the last hidden state from the encoder. After that, we use this C vector as a condition to generate output sequences step by step. So if we write down the equations, it will look like this. So you can see how the output is factorized along all the time steps, and the condition is used in each time step. This framework is straightforward and it's simple. So no matter how long the input sequence is, we can always compress the input sequence information into a single vector. However, there is also an issue because we need to use this C vector across all the time steps when we generate the output. Can we extract different context from the input when we generate different output time steps? The answer is yes, and we can use the attention mechanism to achieve this goal. Suppose we want to generate the second time step Y2 here. We might extract the hidden state from the decoder in the previous time step and feed it back to the encoder. After that, we extract some kind of weight vectors through the softmax layer. Then we do a weighted sum over the input information and produce the vector C2 here. We can use this C2 vector as an input to the decoder and produce the Y2 vector. So this is how the context information can be calculated for the second time step. So notice that we can save the output from the softmax layer. So this is kind of weight information used for the second time step. We can repeat the process for the next time step. So in this case, we feed back the history from the decoder in the second time step, and then we calculate the vector C3 for the output Y3. In general, we can do this for all the time step, and we can write the equations like these. So after we save all the output from the softmax along all the time steps, we can notice the weight calculated by the softmax will gradually change as we generate the output along the time. So the weight is hopefully will also move along the input sequences, as you can see from this picture. So this is known as alignment matrix, and you can find this picture in many papers on TTS or speech recognition. To briefly summarize the attention-based sequence-to-sequence models, we can use these equations. For each time step n, we calculate the softmax weight vector alpha here. And then we use the alpha vector to summarize information from the input. So we do a weighted sum over the h vectors. That gives us the context vector Cn for each time step. With the Cn context, we can generate output Yn and repeat the process for all the time steps. This is generally how the attention-based sequence-to-sequence model works. As you can see from the previous explanation, the attention mechanism is the essential part of sequence-to-sequence TDS model. Due to this reason, there has been so many different types of attention proposed. When I read the papers, I noticed that there are so many different types of attention we can use. Self-attention, forward attention, hard attention, and soft attention. So what is the relationship between different types of attention, and what is the purpose to use a specific attention? So in the next few slides, I will explain them in a more systematic way. Here's my proposal. I organize the attention based on what kind of features they use to compute the alignment, and how do they compute the alignment alpha, and what kind of constraints they need to put on the alignment. So as you can see, to what kind of features to compute the alignment, we can organize attention based on whether they are content-based, whether they are location-aware, or whether they are pure location-based attention. The way to compute the alignment, we can organize attention based according to three groups: additive, dot, and the scaled dot attention. And for the final axis, we can see attentions: the monotonic or forward attention, the local attention, and the global attention. So this is my proposal for organizing the so-called soft attention. Soft attention is not the only group we can find in the literature. If we read the papers, we can find another group so-called hard attention. The difference from the soft attention is that in hot attention, the alignment is treated as latent variables. We need to use all kinds of tools such as dynamic programming and marginalization to calculate the probability and to marginalize the latent variables. I will talk more about the difference between the two groups of attention in the later slides, but for this stage, I will focus on the soft attention. Let's first look at this dot, scaled dot, and additive attention. So these are the three types of attentions which use different ways to compute the alignment matrix. Suppose we are going to compute the output yn for the nth time step. What we have is the decoder state of the previous time step, Sn-1. We also have the features extracted from the input text, which is denoted as h here. So these three types of attention differ in the way to compute the input to the softmax layer. The output of softmax will be the alignment matrix. The first one, the dot attention, directly multiplies these two vectors, the Sn-1 from the decoder, the hm from the encoder. So this is why it is called a dot attention. Scalar dot attention is quite similar, but in this case, we add a scalar d here to change the value of the activation to the softmax layer. The last type of attention is the additive attention. So in this case, we apply linear transformations on the two vectors. After that, we add these two vectors together. So this is the reason why I call it the additive attention. So notice that for all the three types of attentions in this example, we're using the S vector from the decoder, the H vector from the encoder. In other words, we can consider the H as a content of the input. So we multiply the content from the input text with the hidden state from decoder in order to compute the alignment matrix. This brings us to the second question based on which we can classify different types of attention. The question is what kind of features we can use to compute the output alignment. In the previous slide, I explained the dot, scaled dot, and additive attention by using the examples where we use the decoder state and the content vector h to compute alignment. So for these types of methods, we call them content-based attention because they are using the content vector. However, this is not the only way to compute the alignment. The second way is the so-called location-aware attention. As you can see from these two equations, compared with content-based attention, the location-aware attention uses the attention vector from the previous time step. So this attention is aware of the previous alignment, so that's why we call it the location-aware attention. The third type of attention in this group is the so-called location-based attention. So compared with the location-aware attention, we can notice from this equation that the content vector h is removed from the input. So in other words, in the location-based attention, we don't care about the content. We purely compute the attention, the alignment matrix based on the decoder state and the alignment from the previous step. Finally, there is the small variant of the location-based attention. So in this case, we only use the decoder state to compute alignment without using the alignment from the previous time step. From the equations of the four types of attentions, I think you may notice when we compute the attention or the alignment matrix for each output time step, we need to consider all the input time steps. So this leads to the third dimension along which we can classify the attention. Along this dimension, I'd like to explain two types of attention. The first one is the so-called global attention. As the name suggests, when we compute alignment for each output time step, we consider it is possible to get information from all the input time steps. So this matrix, the alignment vector alpha here, has no zero elements. In contrast, when we use the local attention, we consider some of the alignment can be 0. For example, in this case, we only consider to extract information from the input steps in the middle. Now I have explained the 3 dimensions along which we can classify the soft attention. In fact, all the examples I have explained can find their location in this 3D space. But let me give one more concrete example. That is the self-attention. The self-attention is a scalar, this scalar dot attention. It's based on content and it's a global attention. So let's see how it is defined. If we look at the equations of self-attention, we can notice why it's called the scalar dot, global, and content-based attention. But in this case, a special thing about self-attention is that we are extracting both the feature vectors h here and hn here from the input sequences. In other words, we are computing alignment on the input sequences itself. Of course, because we can compute everything in parallel, we can also define a matrix form for the self-attention. So in this case, we formulate the input feature sequences as a matrix, and then we do the scalar dot attention in the matrix form. And the matrix is called the query, key, and the value matrices. In this case, it refers to the same matrix, the H here. So in other words, the self-attention does transformation on the input sequences. Then the output sequences has the same length as the input. In some sense, we can consider the self-attention as a special type of convolutionary neural layers to transform the input into the output with the same length. Of course, we can also use the self-attention for alignment learning. So in this case, it's just a special type of soft attention based on the scalar dot and content-based attention. As you can see from the equations, in this case, we replace the query matrix with the state from the decoder. But the process is quite similar, and we can do everything in parallel by using the matrix multiplication. So by now, I have explained all the 3 dimensions to classify the soft attention and also example based on the self-attention. In fact, there are more ways to combine different types of attentions, and you can find the variants in the paper published by Google this year. Giving the explanation on the soft attention, let's now quickly explain how it works in a TDS system. So for the TDS system, when we use attention-based sequence-to-sequence models, we almost use the same framework as those for the speech translation or machine translation or speech recognition. So in this case, the input is the phonemes or characters. The output is the acoustic feature vector sequences. And we still have the encoder, the attention, and the decoder, which is autoregressive. But of course, we can do something more. For example, adding more layers in the decoder, increase the number of recurrent layers, add the prenet, which receive the feedback from the previous time step in the autoregressive decoder. This is free to choose, but the basic idea is still the attention-based approach to learn alignment between the input and the output. This gives us the basics to understand the first famous TTS system based on sequence-to-sequence model. So this is the Talktron system. As you can see from the picture of the original paper, the architectures of a network can be generally divided into these 3 groups: the decoder, attention, and then the encoder. They just differ how they define the encoder, for example, by using different types of hidden layers to extract information from the input phoneme or character sequences. But the basic idea is still the same: use attention to learn the alignment between the input and the output. In fact, Tacotron is not the only model that uses the sequence-to-sequence based approaches. As far as I read, the first model might be the unpublished work by Alex Graves. If you listen to his talk in 2015, you could notice he plays some samples using the attention-based frameworks, attention-based sequence-to-sequence models, as early as 2015. So after that, in interspeech, there is one paper on Mandarin TTS which first used the attention in a published paper. So after that, it's a Talktron system in 2017. Meanwhile, there are different types of system. For example, the chart waves, the Talktron 2, the DC TTS, and the Deep Voice 3, and Transformer TTS. So all these types of system are based on the attention mechanism. But here, I'd like to also mention one special system, the so-called voice loop, which is also a sequence-to-sequence TTS, but actually use different types of alignment learning, the so-called memory buffer. If you are interested in this model, you can find the illustration in the appendix. To help you to understand the difference between different types of sequence-to-sequence TTS system, I summarize the details and differences in this table across the different TTS systems. There are many details here, for example, in terms of the waveform generator, the acoustic features, the architecture of the decoder and encoder. But let's focus on the attention here. As you can see, for the Tacotron-based system, they mainly use the additive attention, and of course, with a location awareness. There are also other systems, for example, the chart wave, which directly use a location-based attention. And also there is a pure self-attention-based system, that is the Transformer TTS. You can find the details later from the slide. Now I'd like to play some samples published with the papers. So they are from the official website. They are also the data in the public domain. For system trained using their own internal data, I cannot put the samples here, but you can find the samples on their websites.
People look, but no one ever finds it.
The yak was totally out of the blue.
Prosecutors have opened a massive investigation into allegations of fixing games and illegal betting.
Prosecutors have opened a massive investigation into allegations of fixing games and illegal betting.
Some have accepted it as a miracle without any physical explanation.
Some have accepted it as a miracle without any physical explanation.
To be or not to be, that is the question. To be or not to be, that is the question.
After playing the samples, I hope you can have a general impression on how the sequence-to-sequence TTS systems sound like. Of course, the quality might not be as good as what we have heard in the ASWIS booth 2019. There are many different reasons for that. If you want to find other good examples, I suggest the samples on the Talktron and the Transformer, where they used their own internal data to train the systems. After listening to the samples, I think the readers might wonder whether soft attention is good enough for TTS purpose. I think his answer is no. The samples I played are the good samples. There are actually many cases where the sequence-to-sequence based TTS systems do not work. For this case, we need to consider specific attention mechanism that is designed for the TTS. So this leads us to the another group of system which use a monotonic and forward attentions. Before explaining these type of models, I think we need to first explain why the global attention or the global alignment does not work sometimes. Remember that for the global alignment or the global attention, we need to compute alignment between every pair of the input and output time steps. This might be necessary for other tasks such as machine translation, but it might not be necessary for TTS. And this kind of alignment is hard to learn. Sometimes it does not work. So I'd like to play one sample. So this is one sample from the paper from Microsoft Research, where they use the global attention to generate very long sentences. You can hear the sound. So the text transcription is here. So this will be the input.
Crashes /readofs /000000000 /foo. Doc rightiefs /111111111 /foo2. Doc that makes post-processing a little painful. Since the fuzzer reports verves of ziverkoftu roveras
I hope this interesting example can tell you how the soft attention might not work when we use long text as input, and this is the issue we need to solve. So what we can do to alleviate the problems? One thing we can consider is that for text-to-speech, there is some kind of a monotonic relationship between the input and output, because human beings read the text from left to right. So we can use this kind of prior knowledge to constrain the alignment so that we can make it easier for the system to learn the mapping from the input to the output. So the idea looks like this. So this is the motivation behind the monotonic and the forward attention. The central idea of the forward and monotonic attention is to recompute the alignment matrix. So suppose we have computed the alignment matrix like this. So after that, with some kind of prior knowledge, we recompute the alignment matrix to encourage the monotonic alignment. To give you an example of how it works, let's consider this simple task to convert the input x1 to 3 to the output 1 to 3, y1 to 3. Suppose we have used the soft attention and we have computed the alignment for the first time step. So this is where we can introduce a prior knowledge to constrain the alignment learning. So suppose we can only start from the first input time step. So we can build this alignment vector 0 alpha 0 hat here to indicate the initial condition. So in this case, is 1 0 0. Furthermore, we constrain that alignment can only stay at the same input step, or it can only transit from the previous time step to the next time step, like the left to right HMM. Based on these conditions, we can recompute the alignment vector like this, alpha 1 tilde. We can recompute the values. To give you one more example here, if suppose the alpha 1 is equal to 0.5, 0.4, and 0.1. So after the recalculation, we can get a new vector. You can notice how the probability to align the y1 with x3 is reduced from 0.1 to 0.0. So this is how we can use how we do the forward recalculation of the alignment matrix and reduce the impossible alignment during the model training stage. Of course, in the paper, the author proposed other types of mechanism to recompute the alignment matrix, but the central idea is the same. So given the recalculated alignment vector, we can use it to compute the first time step output. We can repeat the process and learn the alignment and then compute the output y1 to y3. Interestingly, if we check the alignment matrix in the paper, we can notice how the forward attention is different from the common soft attention-based approaches. Especially, as you can see from the first row of the alignment matrix, that is the alignment after only one epoch of learning. For the baseline without any constraint, the alignment is just simply random or uniform distribution. For the forward attention with the recalculation of the matrix, you can see how the alignment matrix looks like a monotonic shape. We can also consider these types of monotonic shape as a prior constraint on what we can learn from the input and output data. Based on this example, I think you can understand why the forward attention make it easier for the TTS system to learn the alignment between the input and output. In addition to the forward attention, there are also other types of monotonic attention, for example, using different parametric forms or combine it with local attention. However, I'd like to mention is that the forward or so-called monotonic attention cannot guarantee the attention to be exactly monotonic. There are many reasons to explain that, but I think the fundamental reason is we're still considering the soft attention, where we compute alignment and we summarize the context vector in a deterministic way. So this is the issue we'd like to solve or use hot attention, which I will explain in the later slides. Okay, let's just play some samples to see how the forward attention works. So this is the same text which I played before. So if we use a soft attention, the TTS system does not really work on this sample. Let's listen to how the forward attention-based system works.
Crashes /readofs /000000000 doc writeifs /1111 doc that makes post-processing a little painful since the fuzzer reports crashes in the hierarchical structure mentioned above.
So from this example, you can notice how the forward attention made the system successful to read the later part of this long sentences. This is a good example which shows how forward attention works. But again, as I mentioned in the previous slide, the forward attention is not guaranteed to produce the monotonic alignment. Here's one example from the Microsoft paper.
The preliminary ruling by Judge Lucy in the U.S. District Court for the Northern District of California's to rival chip firms, 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 to rival chip firms. The ruling is a setback for Qualcomm because the chip company and the FTC had jointly asked the judge last month to delay ruling on the issue for up to 30 days while they pursued settlement talks.
This is a funny example. I hope you can notice how the forward attention system repeats the phrase to rival chip firms multiple times. And you can also see this alignment from the picture here. So in this case, alignment is not monotonic. So again, soft attention, the forward attention does not guarantee the monotonic alignment we can learn from the data. Anyway, from the previous samples, I think you can hear how the forward attention can help the TTS system to learn the alignment for the long sentences. Actually, there are many TTS systems using the forward attention, for example, the 4 papers here. I will not play the samples here. If you're interested, you can find the samples on our website or in this slide. So if the soft attention cannot guarantee the monotonic alignment during generation, we have to find another solution. So one potential answer could be the hot attention. Here is my understanding on hot attention. Suppose we have the soft attention alignment matrix. So this matrix tells us the probability that each output time step is aligned with input time step. So from this alignment probability matrix, we may draw a sample monotonic alignment like this. So this is ideal if we want to use monotonic alignment for TTS generation. However, we have to take into consideration that there are multiple candidates for the alignment. For example, the alignment 2 and the alignment 3. And we have different probabilities to draw these samples. Accordingly, during training, we have to take into consideration the uncertainty with different alignment. So in order to evaluate the model likelihood during training, we have to treat the alignment as a latent variable of this probabilistic model. So this idea is very similar to the hidden-Markov model, and as you can imagine during training, we have to use all kinds of dynamic programming, feed-forward or search algorithms to evaluate model likelihood. To give you a more intuitive example of how the hot attention works, we can compare it with the soft attention. As you can see from this picture, for the soft attention, for each output time step, we just directly calculate the weighted sum to extract information from the input. And this is how we do to generate alignment during the generation in the soft attention. And we repeat this operation for all the time steps. In contrast, in the hot attention, we have to draw samples. We have to select only one possible alignment for each time step. Of course, we can use more complicated sampling techniques, such as the beam search or Viterbi decoding, to select the good alignment for the TTS generation. But this is how we do the generation in the hot attention. Compared with soft attention, we don't do weighted sum. Instead, we draw samples. Similarly, in the training stage, we have to use a dynamic programming to summarize all possible alignments in order to evaluate the model likelihood for the hot attention-based models. In contrast, soft attention does not require to do so. We just do the same as what we use for the generation stage. We do the weighted sum for each time step. So the difference between the soft attention and hot attention requires us to use a different space to categorize different techniques for hot attention. That leads to this space, which I think would be easy to understand different kinds of hot attention techniques. However, due to the limited time, I cannot explain the details on hot attention. If you are interested, please find the slides where I explain the hot attention in more details. In terms of the TTS system with hot attention, as far as we know, there is only one group actually using the hot attention with the TTS. That is our group. You can find the reference papers in the website below, and you could also find many details on how we use different types of search and sampling techniques to produce the output alignment from the hot attention-based models. Given the details on soft attention and a brief introduction on the hot attention, we may come to the third group, the hybrid approaches for the sequence-to-sequence TTS models. From the first part of this tutorial, I hope you can understand how the soft attention is easy to implement, but it might not work when we generate long utterances. The hot attention might help to solve this issue because it guarantees a monotonic alignment during generation. However, according to our experiments, the hot attention might not be as accurate as a soft attention. For example, sometimes we may overestimate the duration for the silence. For both soft and hot attention, we compute the alignment probability for each pair of the input and output time steps. For TTS, because the output sequence can be quite long, so this means we have to calculate a large matrix for the alignment probability. This is not easy. Of course, we can do something more efficient. Suppose we can summarize the alignment information from the matrix so that we can know roughly how many output time steps we need to generate for each input token. So by using this information, we can build one probabilistic model for each input token and just estimate how many time steps they need to produce during the generation stage. So this idea is not new. It actually has been used in the HMM and DEM-based system. And actually, this is also the idea behind the hybrid approaches. For the hybrid approaches, they first use a attention-based model to extract the alignment matrix. After that, they summarize information, for example, the duration or how many output time steps we need to repeat for each input token. After summarizing this information, we can train the duration model directly for each input token. During the generation stage, we can directly plug in the trained duration model. As you can see from this picture, we just need to predict how many output time steps we need to repeat for each input token. Given this duration information, we can do the upsampling just by duplicating each input vectors. So the input to the decoder will be well aligned with the output sequences we want to generate. We can use normal neural networks such as feed-forward, recurrent, or autoregressive neural networks to convert the input to the output acoustic feature sequences. Here are some TTS systems using the hybrid approaches. The fast speech uses soft attention to extract the duration, while the aligned TTS and the other system use different kinds of techniques to extract the duration. I'd like to play some samples extracted from the published papers. I will play just one sample for each system from fast speech and to fast speech 2.
The chapel yard led to the chapel, and on the staircase were 2 rooms frequently set apart for the king's witnesses. The chapel yard led to the chapel, and on the staircase were 2 rooms frequently set apart for the king's witnesses.
Although I only played the short samples here, but I think you can find the long sentences on their website. What I want to see here from the example is that by using hybrid approaches, we can generate the synthetic speech with a quite robust duration. I think that is one strong point about hybrid approaches. Okay, let's come to the summary. In this tutorial, I first explained the pipeline TTS system, including the HMM and DM-based systems. In the pipeline TTS, we need to use the front end to extract linguistic information from the input text. After that, we need the duration model to predict the duration for each input unit. Following that, we need the acoustic model and the waveform generators to convert the linguistic features into final waveform. In 2016, Google DeepMind proposed the WaveNet. Although it is not explained in this tutorial, I'd like to mention that the original WaveNet still needs the front end and the duration model. So it achieves the astonishing performance because it uses a single network to directly convert the linguistic features into the waveform sampling points directly. This solves the issues or the artifact when we use the conventional waveform generators like the vocoders. Different from these 2 types of TTS system, the sequence-to-sequence model uses a single model to convert the input text into the acoustic features. They use a single model to do alignment learning, to do the duration modeling, and the acoustic modeling. In fact, many sequence-to-sequence models also use WaveNet-like waveform generators to further improve the quality of the synthesized speech. If we summarize the difference from the pipeline system to the sequence-to-sequence system, I think there are 4 aspects. The first one is we replace the conventional front end in the pipeline system with a trainable implicit front end in the sequence-to-sequence model. Second, instead of using external duration model, we may jointly do the duration modeling with the sequence-to-sequence mapping. Third point is the acoustic models. Although it is not explained in this tutorial, actually most of the sequence-to-sequence model use the so-called autoregressive decoding. So we produce one output time step conditioned on the previous time step. The last point is the neural waveform models, as I mentioned in the previous slide. Many of the sequence-to-sequence models use neural waveform models like the WaveNet. The first 3 types of differences are implemented through the attention-based sequence-to-sequence models. So in this tutorial, we focused on the attention mechanism. We first explained the soft attention. We also grouped the soft attention approaches based on the 3 dimensions. What kind of features we use to calculate the alignment matrix, how do we calculate alignment, and what kind of constraint we can put on the alignment. We also mentioned the shortcoming of the soft attention. It does not guarantee the monotonic structures. That motivates the hot attention-based approach. However, the hot attention might not be accurate enough to produce natural speech. That gives us to the third possible solution, the hybrid approach, where we don't use the attention during the generation. All the four aspects are quite essential to the performance of the sequence-to-sequence TTS models. Of course, we may wonder what is the most important factor that contributed to the performance of sequence-to-sequence model. To answer that, Oliver and his colleagues designed an experiment, and they tried to analyze the impact of each of the factors on the quality of generated speech from the sequence-to-sequence models. It's recommended to read their paper to understand why the sequence-to-sequence model outperformed the TTS pipeline systems. Before we end this tutorial, let me briefly mention all the research topics based on the sequence-to-sequence TTS models. The first topic is the neural waveform models that has been used in many sequence-to-sequence models. Due to the limited time, I cannot explain the neural waveform models, but you can find reference papers in the reading list. Another topic is the speaker style and emotion modeling in the sequence-to-sequence models. Porosity is also a hot topic in sequence-to-sequence modeling. In terms of multi-speaker modeling, I think most of the sequence-to-sequence models are quite straightforward. They either jointly train the speaker vectors with the sequence-to-sequence model, or they use separate speaker model to extract the speaker vectors from the reference speech. So this is a so-called zero-shot learning for multi-speaker TTS. In terms of porosity, there are papers focusing on segmental porosity, for example, the lexicon tone or the pitch accent. So these are the most of these papers are focusing on the pitch accent language or tonal language, such as Mandarin or Japanese. In terms of the supra-segmental variations, there are also papers combining the porosity embedding with the Talktron-based systems, also systems using the variational autoencoders to extract the porosity embeddings from the reference speech. Finally, I'd like to mention another direction for the TTS research, that is the TTS for entertainment. So in this paper, the authors use the traditional Japanese comedy data to train the TTS system. So the goal of this kind of TTS system is not only the speech communication, but also to entertain the audience. This is the end of this tutorial. You can find this slide on my GitHub page. It's recommended to check the unexplained slides, the reading list, and the appendix. Thank you for listening.